NanoHub U, online instruction.
Hello and welcome back. We're now in the middle of Unit 3. We're talking about ballistic nanotransistors. In the last lecture, we derived the IV characteristic of a ballistic MOSFET. What I'd like to do in this lecture is just take a little closer look at the velocity at the top of the barrier in these devices. So remember, we write our drain current expression as the product of charge times velocity. And what I'd like to do in this lecture is to focus on this velocity, understand how it varies with gate voltage and how it varies with drain voltage, this velocity at the top of the barrier or the virtual source. So here's an energy band diagram. We are going to focus on the virtual source, the top of the energy barrier, and we're going to ask what is the velocity at the top of the barrier and how does it vary as we increase the drain voltage. We'll also be interested in whether there's a gate voltage dependence to that velocity as well. So here's the IV expression that we developed for the current voltage characteristics of a ballistic MOSFET. We know that current is charge times velocity. All we have to do is to compare these two expressions and voila, we have our expression for the average velocity at the top of the barrier as a function of the drain voltage. Remember, we're assuming non-degenerate carrier statistics here to keep the math simple, but the same general considerations apply when we use Fermi-Dirac statistics. So let's take a look. Let's plot this average velocity at the top of the barrier as a function of drain to source voltage. We'll get a characteristic that will look like this. For low drain to source voltages, the velocity is proportional to the voltage. For high drain to source voltage, the velocity saturates. So let's talk about both regimes, and let's begin with this linear regime. So in the linear regime, we can begin with our general expression for this curve. We'll assume that the drain voltage is small compared to KT, which means I can expand the arguments. The arguments of these exponentials are small. I can expand the exponential for small argument. And when I do that, we'll get a simple expression for the average velocity, and we will find that it's proportional to the drain voltage, just as we see in this curve. Now, if I would manipulate this a little bit, let me divide by L. So I have drain voltage divided by L, and then I have to multiply by L so that I don't change the formula. And if I do it that way, you can see that there's a group of terms here that I can lump together that have the units of centimeters squared per volt second. We've seen this before. We're going to call this the ballistic mobility. And maybe we can talk a little bit about what that means in a minute. So the bottom line is that in this regime, remember we're in a ballistic MOSFET with no scattering, we can write the average velocity as ballistic mobility times the electric field in the channel. Mu B times electric field in the x direction. That's exactly the same expression we would use for a large diffusive semiconductor with lots of scattering, but this is a ballistic device. So that's quite interesting. So what does this ballistic mobility mean? Now here's our nano device. It has some length L. Okay. Now we will discuss scattering and we'll discuss mobility a little more in Unit 4 when we add scattering to our picture. But for now, let me just give you this expression for the mobility in terms of the thermal velocity, kT over q, and this quantity lambda naught. By lambda naught, I mean the average distance between scattering events. It's the average distance that an electron travels before it backscatters or goes in some random direction. So we call it the average mean free path for backscattering. Now it's sort of intuitively sensible that the longer the distance between scattering events, the easier it is for electrons to get through a material. And if it's easier to get through, the mobility is higher. So it makes sense to say that the mobility is proportional to the mean free path for backscattering. Now, if we look at this quantity that we've derived, this ballistic mobility, all we've done is to replace this average distance between backscattering events that an electron would experience in a bulk semiconductor. Now we're in a nano device. We've just replaced that average mean free path by the length of the channel. So the picture is this. Electrons go across the channel without scattering. That's what we mean by a ballistic MOSFET. But there is a lot of scattering initially in the source. Then they travel across the channel and they scatter immediately because there's a lot of scattering in the drain. So the distance between scattering events, since the region in between is ballistic, the distance between scattering events is simply the length of the channel. So it makes sense in this nano device that we should replace the mean free path for scattering by the channel length. And that's one way that we can make sense of this ballistic mobility. Okay, we have this velocity versus drain voltage characteristic. Let's look now up here at the high drain voltage regime where the velocity saturates at the thermal velocity. Okay, so this is really quite interesting. The velocity is saturating in a ballistic MOSFET. In the sort of textbook derivation of the velocity saturation characteristics of transistors, we think of velocity saturation as occurring near the drain, where the electric field is high, and we have high field velocity saturation due to the scattering of the energetic carriers in that high electric field. But we are assuming a ballistic MOSFET with no scattering. So it's curious that the velocity saturates. And in fact, it doesn't saturate at the drain end where the electric field is high. It saturates at the top of the barrier. Remember, the electric field is proportional to the slope of the energy band. And the electric field is zero. So the velocity saturates not at the drain end, it saturates at the source end. It saturates not where the electric field is high, it saturates where the electric field is zero. So that's really interesting. Let's talk about that a little bit. But first, how would you know if you're dealing with a velocity saturation? How would you know if you're dealing with a MOSFET that is experiencing velocity saturation? We discussed this briefly way back in Unit 1. If you see an IV characteristic and you see that the saturation current goes linearly with Vg minus Vt, you say, aha, this is a velocity saturated MOSFET. So that's our signature of velocity saturation when we measure the characteristics of a MOSFET. In the traditional diffusive model, that saturation occurs because of all of the scattering. It's the high field saturation velocity of electrons in bulk silicon. We just apply it to this small device. In our ballistic model, we have an equation that is almost identical, but we have a different velocity. And that velocity is the unidirectional thermal velocity. So let's see if we can understand this a little bit. And to do that, we've talked about how the electrons are distributed in velocity space briefly. Let me just remind you of that. If I assume non-degenerate or Maxwellian carrier statistics just to make life easy for us, then we can simplify the Fermi function into an exponential. If we assume parabolic energy bands, then V squared is going to be Vx squared plus Vy squared. It corresponds to the motion of the electrons in the xy plane of the channel. They're two-dimensional electrons. And we end up concluding that the electrons are distributed in this Gaussian or Maxwellian distribution of velocities. If we plot it in the xy plane, we get a nice symmetrical distribution. This nice symmetrical distribution is maintained in a bulk semiconductor because of all of the scattering that is going on and all of the exchange of energy and momentum between the electrons and the phonons, and everything comes to equilibrium, and we get this Maxwellian distribution with the spread of that Gaussian being related to the thermal energy kT. Okay, that's what we see in thermal equilibrium. What do we see in a ballistic nanoscale MOSFET? So these are numerical simulations we're going to look at. High gate voltage, a number of different drain voltages. We are going to look at the top of the barrier and see if we can understand why the velocity increases as a function of drain voltage there and why it saturates there. Okay, so these are distributions or plots of how the electrons are distributed in velocity space in these xy directions at the top of the barrier, and they come from these numerical simulations. And we're showing results at 4 different drain voltages. So let's look at this. At 0 drain voltage, we get our nice equilibrium Maxwellian distribution of velocities. Every positive velocity electron is canceled by a negative velocity electron. There's no net velocity. The velocity is 0, the current is 0, which it should be when the drain voltage is 0. Now, it's kind of interesting. You may ask, how is this thermal equilibrium maintained when we don't have scattering to randomize everything with the lattice? Well, the answer is that the positive half of this distribution came in from the thermal equilibrium source, where scattering ensured that we were in thermal equilibrium. The negative half of this velocity distribution came in from the drain, where the strong scattering maintained thermodynamic equilibrium in the drain. So this is really two halves of an equilibrium thermal distribution, one entering the device from the source, the other entering the device from the drain. Put the two together, it looks just like an equilibrium distribution of velocities in a bulk semiconductor. Okay, now let's add a small drain voltage. It makes it a little bit harder for the electrons from the drain to populate the states at the top of the barrier. Or if we think about it in a thermionic emission model, there's a higher barrier to hop over and get to the top of the barrier. So if we look at this distribution of velocities, we see that the positive half doesn't seem to have changed. The electrons are coming in from the source just the way they did before. But the negative half is significantly smaller. So now all of the positive velocities aren't canceled by the negative velocities. The average velocity increases. This is the region where the velocity begins to increase linearly with drain voltage. You add an even higher drain voltage, you see an even smaller number of negative velocity electrons. The net positive velocity is even bigger. You add an even bigger voltage, and now we can't see any negative velocity electrons. The Fermi level in the drain has been pulled down so low that there is no probability of the negative velocity states at the top of the barrier being occupied. We only have positive velocity states. The velocity that we see is just the average velocity of all of those positive velocity states, and now it can't change. If we increase the drain voltage more, we'll continue to send in electrons from the source with their fixed positive velocity. We have no negative velocity electrons, so the average velocity is constant. This is the mechanism of velocity saturation in a nanoscale MOSFET. So the key velocity then we're interested in under on-current conditions is what is the average velocity of that positive half. Now I'm simply showing you the expression for the IV characteristics in the degenerate case. This is the complete IV characteristic. If we go to high drain bias, then these arguments simplify. Under high drain bias, we pull the Fermi level way down in the drain. The Fermi-Dirac integrals become exponentials. It becomes e to the minus x, where x is very large. This term goes to 1, and we're left with an average velocity that is given by this expression. Now, if I write this as WQ average velocity at the top of the barrier, we'll call this average velocity at the top of the barrier the ballistic injection velocity. So this is a really important quantity for us when we think about transistors. It's this unidirectional thermal velocity that we've talked about before, V sub t, times a ratio of Fermi-Dirac integrals. For a non-degenerate semiconductor, all Fermi-Dirac integrals reduce to exponentials. This second factor here becomes 1, and the ballistic injection velocity is just V sub t, the unidirectional thermal velocity. So I want to remind you that we're talking about two-dimensional carriers here. If I were to do this calculation for a nanowire MOSFET and I had 1D carriers, the same general considerations would apply, but I would see Fermi-Dirac integrals of different orders. So you should keep that in mind. So just the takeaway message here is that the velocity under on-current conditions is something that we're going to call the ballistic injection velocity. Physically, it corresponds to the average velocity of this positive half of the electron velocity distribution that entered from the source. It depends on the location of the Fermi level when we can't assume non-degenerate conditions. So if we plot it as a function of the electron density at the top of the barrier, we'll get a curve that looks like this. And since the electron density is controlled by the gate voltage, we will have a gate voltage dependent injection velocity. If I look for low numbers of inversion carriers, maybe sub-threshold operation, the Fermi-Dirac integrals, this ratio here reduces to 1, and the injection velocity is simply this unidirectional thermal velocity. If I go to very high carrier densities, and 10 to the 13th is sort of the maximum carrier density that we realistically encounter in MOSFETs. If I go even a little higher than that, I would be at the fully degenerate limit, where all of the states below the Fermi level could be considered filled, all the states above could be considered empty, and then it's easy to work out the ballistic injection velocity. It is just some fraction of the Fermi velocity. And you'll recall that the Fermi velocity is the velocity of electrons at the Fermi energy. In between, it's given by this expression which goes smoothly between those two limits and depends on where the Fermi level is located with respect to the top of the barrier. Okay, so just to summarize that, when we can assume Maxwell-Boltzmann statistics, the velocity under on-current conditions is the ballistic injection velocity. It's just this unidirectional thermal velocity, independent of gate voltage. When we have to consider Fermi-Dirac statistics, which really we should do above threshold all the time, we find that the ballistic injection velocity involves a ratio of Fermi-Dirac integrals. This term eta Fs is just a measure of where the Fermi level in the source is with respect to the bottom of the conduction band at the top of the barrier. Now, the way this would work in practice is that we would fix the charge density at the top of the barrier with a gate voltage. Then we would deduce where the Fermi level is with respect to the bottom of the conduction band. Then we could compute the ballistic injection velocity. And remember again, we're doing this calculation for 2D carriers in the XY plane in a planar MOSFET. We're assuming parabolic energy bands. If those assumptions are relaxed or different for a device that we're considering, we'll get results that look different, different orders of Fermi-Dirac integrals, for example, but the same general considerations will apply. So these are the key points. The signature of velocity saturation when we measure the IV characteristics of a MOSFET is that the saturated current goes linearly with Vg minus Vt. The velocity saturates in a MOSFET, which was really a bit of a surprise to people when we first started looking at ballistic MOSFETs. But it saturates not at the drain end, but at the top of the barrier. It saturates not where the electric field is high, it saturates where the electric field is zero. And the ballistic injection velocity, which is a key parameter determining how much on current we get, increases with increasing electron density when we encounter non-degenerate carrier statistics. Okay, so we now have an understanding of the IV characteristics from the last lecture. We understand a little more deeply this average velocity at the top of the barrier from this lecture. It's time for us now to revisit our virtual source model and connect this ballistic model that we've just developed to that virtual source model. We'll do that in the next lecture. Thank you.